Good morning, good afternoon, good evening, everyone. Let me start our meeting. Today we have the speaker Valery Nakaryakov. Valery got his PhD in plasma physics at the Institute for Applied Physics of the Russian Academy of Science in 1993. And since 1995, he has been in the UK. Since 1999, he is holding a permanent academic position at the University of Warwick, and now he is full professor of physics. Valery has held prestigious Royal Society Senior Fellowship and the European Research Council Advanced Fellowship, and served as president of the European Solar Physics Division, chair of the UK Solar Physics, and a council member of the Royal Astronomical Society. In 2014, he gained a Payne Gaposchkin Medal of Institute of Physics, which is issued once in 2 years for the best achievements in plasma physics. Valery's main research interests are connected with MHD waves and oscillations and MHD seismology of the solar corona. So please go ahead, Valery, you have your 45 minutes for presentation and then for
Okay, so Gregory, thank you very much. So first of all, again, so I would like to thank you for inviting me to give a talk at your webinar. It's a great pleasure and I'm honored. And today I'll be talking about one of my main research avenues, research activities of our research team here at Warwick, MHD diagnostics of the corona of the sun, so by kink oscillations. So first of all, I'll show a movie which possibly you have seen a number of times. So this is a trace image taken in the extreme ultraviolet band, and so a movie clearly showing oscillating loops excited by some impulsive energy release in an active region nearby. So, and we can also see that those loops are magnetically not linked to the epicenter of the energy release. So the first observation was made about 21.5 years ago. So and first papers were published in 1999. So last year we had about 20 years anniversary of the beginning of the study of kink oscillations. So what you can see are quasi-periodic displacements which rapidly decay of coronal loops. So typical periods are several minutes, but I'll tell much more about the statistics a bit later. But now possibly I should state that what we see in this movie, what we watch, perhaps is an example of the longest electromagnetic waves which are resolved simultaneously in time and in space, meaning we do resolve well the period of oscillations, and also simultaneously we resolve well the wavelength of the oscillation, which is double the length of the oscillating loop, if we are talking about the fundamental harmonic of this oscillation. So, and now we have several hundred examples of these oscillations. And actually, since the first observation, the observational discovery of this kind of wave activity of the corona, those waves been attracting major attention in the context of coronal heating and MHD diagnostics, MHD seismology of the corona, while possibly I should mention that the energy released by this oscillation, meaning we see the decaying oscillation, so hence the energy of the mechanical displacement goes to the internal energy in the end. So the energy of this oscillation is less than a nanoflare. So despite the amplitude is sufficiently high, so hence actually those waves or those oscillations definitely do not play any role in heating of the corona because they are sufficiently rare, even so despite we have several hundred examples, but say over the whole pair of solar cycles. So anyway, those waves attract attention mainly as the seismological probe of the corona, and so just reminding that seismology is MHD waves. MHD wave are based on diagnostics of natural plasma environments. So in the corona, we are talking about coronal seismology. So it's one of the dedicated aims of SDO AIA, which has been providing us with excellent data for already more than 10 years. So talking about future missions, so it's one of the science objectives of a future European Space Agency Proba 3 Aspects instrument. NASA and Korean coronagraph to be installed on the International Space Station, so HI-C project, etc. And also, so MHD seismology is named as one of the key methods proposed to be developed in the report of Understanding Space Weather to Shield Society, so the global roadmap for 2015-2025, meaning so the efforts we have in coronal seismology are consistent with the main, say, research avenue of our research community. So also, so sometimes MHD seismology is called magnetoseismology, but we should possibly not use this term because it's so just mimic of the magnetoseismology or magnetospheric seismology. So the term which is used in our neighboring science, so MHD wave probing of the magnetosphere of the Earth, and also MHD spectroscopy of laboratory plasmas, in particular tokamaks. So it's another very intensively developing research avenue. So, and in this talk, as I have only 45 minutes, I'll mainly present some observational results, some statistical results, and also articulate a few, say, current trends and future problems, so which possibly are on the cutting edge of the research in our sub-community. So first of all, so the terminology which I'm going to use in my talk, so we call it a standard theory. It is based upon the theory describing interaction of MHD waves with plasma structures, so which initially was constructed by Zaitsev and Stepanov, so then by Bernie Roberts and colleagues. And so in principle, so this is a good, say, third year undergraduate student problem. So if you have a plasma cylinder, so which is filled in with the plasma of, so with different properties, surrounded with the plasma with different properties, and also penetrated by the magnetic field inside and also outside. All physical parameters can experience a jump at the boundary of this flux tube. So hence we begin with MHD equations. We determine the equilibrium. We linearize, so the MHD equations inside and outside with respect to this equilibrium, apply boundary conditions, and in the end we arrive at the dispersion relation, which is shown here. So because of the cylindrical geometry, so we have Bessel functions in our dispersion relation. So here, so there are modified Bessel functions and so-called Macdonald functions and their derivatives. So, and so this is an algebraic transcendental equation which links parameters of MHD perturbations, namely, so the frequency and the axial wave number with the parameters of the plasma inside and outside the flux tube. Also here we have some index M, so just here, so which is the azimuthal wave number, so corresponding to the azimuthal symmetry of the perturbation. So this theory is still being developed, so because so there are a lot of interesting limiting cases, but so the main outcome of this theory is the existence of different modes, so which we separate by their geometry, by the azimuthal symmetry. So, and also appearance of the dispersion. So wave dispersion, meaning so the group and the phase speed of the perturbations depend upon the frequency or the wave number. So also, so just mentioning, so just for clarity, so in this talk I'll be using some characteristic speeds. So two natural characteristic speeds of the coronal plasma are the sound speed, which is a measure of the temperature, so and the Alfvén speed, which is the ratio of the magnetic field and the root of the density. Also, we can introduce the fast speed, so just traditional MHD fast speed. So the cusp or tube speed, which is combination of the sound and Alfvén speeds. So, and what is important for kink oscillations especially is the kink speed, which is the phase speed of the perturbations of kink waves in the long wavelength limit. So, and in the low beta limit, so which is typical for coronal active regions, so the kink speed so could be reduced to the Alfvén speed inside the, say, oscillating cylinder, for example, a flux tube, so multiplied by this square root, so which contains the density contrast inside and outside the flux tube. So this is just the terminology which I'm going to use, and now just illustrating what I'm talking about. So this is the plasma cylinder perturbed by different MHD modes. So different snapshots correspond to perturbations with different azimuthal wave number. So there is the sausage wave number, so various ballooning perturbations. So this is the King oscillation, which corresponds to m equals to 1. So there is the azimuthal wave number. So, and we can see that the perturbation is axially antisymmetric. So here I show the linear polarization, and just so make it linking this with the movie which I showed. So we can consider King oscillation of a plasma cylinder which represents an oscillating loop. So with foot points somewhere here and there. So this is the body of the oscillating loop. So this is the linear polarization. Usually in our studies, we practically exclusively consider the linear polarization, while obviously as any transverse wave, a King wave may have a circular polarization or elliptical polarization. And here I just show one of the examples of such polarizations, which sometimes we can call an helical perturbation. But all those modes actually, linearly polarized and circularly polarized, are King waves with quite simple properties. So King waves are guided fast magnetoacoustic waves. So according to the derivation by Zaitsev and Stepanov and Roberts and colleagues. So this is a snapshot of the perturbation of a plasma cylinder. So you can see the King displacement of the cylinder, in this case upwards, so with the nodes of the perturbation here and there. And the color shows the perturbations of the density of the plasma. So we can see that the plasma is not uniform inside the cylinder. So there is the movement of the plasma, say in the transverse direction, and the divergence of the velocity is non-zero in such a mode. So hence actually, there is the illustration that this mode is essentially compressive, and it must not be confused with the Alfvén wave. So several, maybe 10, 12 years ago, we had some debates in the literature about the nature of those waves, but now I think it's settled down. So those waves are different from Alfvén waves because they're essentially compressive, dispersive, so they are collective, so meaning the perturbation of the plasma, so everywhere in the cylinder is involved in the mode. Also, the mode consists of the global perturbation of the plasma everywhere in the oscillating loop, so hence it's a fast wave. So, and also, just in the context of what I'm going to tell you next, so this wave has a very interesting property. So if the profile of the density of the plasma in the radial direction is smooth, in this case, we may have the effect of linear coupling of this mode with Alfvén waves, true Alfvén waves of the torsional symmetry. So this is the famous effect of resonant absorption, with possibly several hundred research papers published by different research groups in the last 30, 40 years. So in this case, the King motion, so in this case, the wave is polarized linearly in the horizontal direction. So at some certain narrow layers, the phase speed of the wave can coincide with the internal Alfvén speed at those locations. So hence we have the coupling between the collective King oscillation, which we see in observations, and in principle invisible King motion, very narrow, sitting at a certain magnetic surfaces or surfaces of the constant Alfvén speed. So, and in this case, the apparent damping of King oscillations may be considered as the transfer of energy from the collective King oscillation to the unresolved torsional motions. So hence actually the damping of waves is not real dissipation, it's just the energy transfer, and so then the energy dissipates by some mechanisms, but unfortunately we don't see this part of the story, while the effect of resonant absorption is well known in numerical simulations and also in laboratory plasma experiments where this phenomenon can be seen, so with just antennae and other probing. So mathematically, it's possibly one of the few equations I'm going to show in my talk. So the effect of resonant absorption is described by a coupled set of two ordinary differential equations. So the only independent variable here is the radial coordinate, and so there is the Fourier transform with respect to all other variables. So what is important here, we can see the coefficient d, so which may become 0. So when the phase speed, axial phase speed, coincides with the local Alfvén speed, and also coincides with the local cusp or tube speed. So from the mathematical point of view, so if d goes to 0, so at those two resonances, so the set of equations become singular, and so we need to apply some certain boundary conditions at the layers where the resonant conditions are fulfilled. So this theory been designed by Joe Holweg, by Marcel Goossens, by Michael Ruderman, by Bernie Roberts, and a number of their pupils and disciples. So now the formula which is usually taken as the standard formula, which links the damping time or coupling time of the kink mode and torsional oscillations divided by the period of oscillations, so links this, let's say, generalized quality factor of the oscillation with the density contrast inside and outside, so the oscillating cylinder, and so the kind of smoothness or stiffness of the radial profile of the flux tube. So, and in principle, just substituting parameters of coronal loops, we can get different quality factors, different values of the ratios of the damping time to the period of oscillations. But actually, so just you will see that for some reason in observations, usually we see this ratio of about 3 to 5, which we still don't understand, but at least so the theory can explain this value just if you follow this mathematics. These days we have, as I've mentioned, quite a few observations of kink oscillations with SDO-AIA. So just one of the examples, so a movie made by my colleague Giuseppe Nistico. You can see the oscillating loop somewhere here. Say observational slits across the loop along the direction of the loop displacement, transverse displacement. So we are getting the oscillatory pattern, so as a function, as the displacement along the loop as a function of time. So here time is in seconds and displacement is in kilometers. So, and we have quite a few observations of this kind. So, and then we, having this time distance map again, so there's the displacement of the loop along the slit, and this is time, so this time in minutes. So you can best fit the decaying pattern by some guessed analytical function. For example, here it is the just decaying sinusoid, exponentially decaying sinusoid. So by best fitting using sometimes quite sophisticated techniques based upon the Markov chain Monte Carlo technique or say other fancy methods, you get in the oscillation period, decay time. So in the presence of multiple harmonics, you're getting actually those parameters for different harmonics. So which is quite promising and nice. So, and actually about 20 years ago, we proposed and implemented for the first time a technique for the seismological estimation of the magnetic field by kink oscillations. So in the yellow ovals, there are observables, so the geometrical size of the loop, so the period of oscillation, the information that the oscillation is standing because different segments of the loop oscillate in phase, also the density contrast, which in principle we can get from spectroscopic observations or from the emission measure. So, and following this, say, pattern of calculations, we estimating the kink speed and then the Alfvén speed. And if we know the density of the oscillating loop, so we get the coronal magnetic field. So actually what I should stress, so this coronal magnetic field is at the location where the amplitude of our kink oscillation is the highest. In other words, it's near the apex of the oscillating loop in the case of the fundamental harmonic. So it's not near the foot points where the oscillation has the nodes, but where the oscillation, so the displacement has a maximum. So now just a few recent, say, breakthroughs in the understanding of what is going on. So first of all, using statistical, say, catalogs of properties of King oscillations, at last, so we managed to understand what does excite King oscillations. Because from the very beginning, so 20 years ago, so we believed that it's connected with a blast wave excited by a flare or something like that. But now, so just showing this movie, you can clearly see that there is some eruption, so some plasma going in this direction, which mechanically displaces so the neighboring loops from the equilibrium, and then those loops oscillate around this equilibrium. So it's like a pendulum, so which is just displaced from the minimal point, minimal energy point, released, and then oscillates freely around the equilibrium. So here we illustrated, so in that paper, so we illustrated this mechanism by this sequence of sketches. So this is the loop. So there is some low coronal eruption, which displaces the loop from the equilibrium, goes up, so it can be failed eruption, could be real eruption, so it doesn't matter. So, but what is important, so the loop is displaced from the equilibrium and then oscillate around the
Valery, what is LCE?
Low coronal eruption.
Okay.
So no, here I show the, say, magnetic torus eruption, but it could be something like that. So of course, there are observations showing that this mechanism is not a unique observation. So there's another famous event known as the Harmonica event. You can see the side view of a coronal post-flaring arcade. So there is some eruption here, so which somehow excites King oscillations, which we are clearly seeing near the apexes of these arcade loops. So, but clearly, so it's not the mechanism which I described. Meaning, so the jury is still out, but in about 95% of analyzed cases, so the low coronal eruption, say, mechanism for the excitation is valid and so demonstrated statistically. I've mentioned the statistics several times now, just showing the results of the most comprehensive catalog of King oscillations, decaying King oscillations, which we published last April in the Astrophysical Journal supplement series. So this is a histogram showing the distribution of apparent amplitudes of the oscillations, so number of cases here, and amplitudes in megameters. So I must stress it's the apparent or projected amplitude, so which of course should not be confused with the real amplitude. So what is important, so this apparent amplitude is always smaller than the actual amplitude of the oscillation because of the projection effect. So we can see that the typical, say, values of the amplitudes are several megameters, while even, say, higher amplitudes sometimes are detected. So this is the so similar histogram, but with respect to the period of oscillations. So you can see that so the period of oscillations has a maximum in the vicinity of 5 minutes, but later I'll show that it is absolutely not connected with P modes or say photospheric 5-minute oscillations. So it's just the parameter, so which is controlled by the length of the oscillating loop, by the density of the plasma in this loop, and by the strength of the magnetic field. So hence it's just a coincidence. No, and also we see a sufficiently broad range of so those periods from a few minutes to, well, up to 20-25 minutes in general. So this is the same, but distribution with respect to the loop length. So we can see that both short and long loops show systematically, so King oscillations, decaying King oscillations. So here you can see, actually, I didn't mention the black and blue colors, but those colors, so just a combination of two catalogs, and so in principle, so the final answer is just the total distribution. So just if you follow the envelope of those black distribution, it shows the statistics. So hence, in principle, we can see that King oscillation phenomenon is broadband, so and is not, say, connected with loops of certain length. So and typical periods are several minutes. So then another important result, was also recently obtained using this statistical data. So this is the breakdown of the distribution of the period of oscillation versus the loop length. So for each event of kink oscillation, we measure the length of the oscillating loop somehow, and also measure the period of the oscillation. And we can clearly see that so the period increases with the loop length. So, and so we can also make a histogram of the gradients of those, which can go through the origin and each observation, so which would give speed. So we can see that the distribution of kinks is, say, maximum at about 1300 kilometers per second, and brought from let's say 500 kilometers per second to about 3000 kilometers per second, possibly responding to the distribution of the coronal magnetic field and so lengths of loops and other interesting parameters. So what I should say, so this statistics is gathered during 15 years, because it was published in 2016, and actually now we have more recent data, so just including results obtained after 2016, but so statistics is more or less the same. And here we did not make any, say, discrimination between results obtained during the solar maximum and solar minimum. And it would be an interesting future work just to see how those parameters of the corona vary with the solar cycle. Because so this statistics of several hundred events allows us already to trace the evolution of properties of coronal loops, coronal active regions with the solar cycle. So this is the new statistics which I mentioned, and measured kink speeds. So again, this is the most comprehensive catalog, but results are similar to what we got before. So from a few hundred kilometers per second to say a few thousand kilometers per second. So then, the mechanism for damping recently got some, or generated some interest again, because in principle the community tend to believe that the resonant absorption, the linear coupling between collective kink oscillations and unresolved torsional alphenic motions, is the main reason for the dissipation. But actually now we have more interesting statistical results. So first of all, it's a result of Erwin Verwichte, published several years ago. So this is the scaling of the damping time with the period of oscillations. You can see there is some signature of the linear dependence. It's a log-log plot, and the best scaling is when the damping time scales as the period to the power of 1. Which is consistent with resonant absorption. However, of course, the distribution is sufficiently broad. So, and now just most recent statistics, now it's a linear plot, so damping time versus the period of oscillations. Again, roughly speaking, the data cloud could be approximated by a straight line. So meaning, the damping time scales linearly with the period of oscillations. So this is important because if we are talking about dissipation by, say, finite resistivity, finite viscosity of the plasma, in this case, the scaling should be parabolic. So it should be period squared. But we have a clearly, say, linear scaling. So despite the broad, broadness of the data cloud, hence, in principle, it seems to be the indication that indeed resonant absorption is the mechanism for damping. But recently, again, some new results were obtained. So this is the scaling of the quality factor of the oscillations, meaning the damping time versus period. So this is what I mentioned, with the apparent or projected amplitude of the displacement. So we must again stress that the apparent amplitude is always lower than the actual amplitude because of the line of sight projection. So we see that the data cloud is clearly shows the decrease in the quality factor with the increase in the apparent amplitude. So it could be seen in the linear plot, and also there is the log-log plot. So we can see this boundary of this data cloud. And why do we best fit the boundary of this data cloud? So it's important because again, the apparent amplitude cannot be higher than the actual amplitude. It is always lower. So hence actually the statistics of the dependence of the damping time versus period on the amplitude so should be approximated by this outer boundary of the data cloud. So we clearly see that so the effect of damping of Kink oscillations depends upon the amplitude. So which means so the effect of damping of Kink oscillations is nonlinear. It depends upon the amplitude. So linear, so the effect of resonant absorption is linear. So hence actually what should now develop is the nonlinear theory of resonant absorption or account for other, say, new phenomena, new effects which could lead to the damping and be more consistent with the observed scaling. So in principle, of course, in theory, so we have some ideas what could be those nonlinear effects. So in particular was shown by Jamet Terradas about 12 years ago. So there is the secondary instability, so which is the Kelvin-Helmholtz instability of the shear flow at the resonant layer. So in this case, so the boundary of the oscillating cylinder becomes destabilized. So there is the generation of alphanic vortices. So here, so John showed it in both perturbations of the density and perturbation of the vorticity. So, and we clearly see that so the energy goes to some, say, turbulization of the plasma. So in principle, there are quite a few recent numerical simulations which confirm so the importance of this effect. But on the other hand, so there is some actually quite a few open questions. In particular, the loop oscillates, so the oscillation decays, but so the apparent properties of the cross section of the flux tube of the loop they don't change. Meaning observationally so far we don't have a clear evidence of this Kelvin-Helmholtz instability and of the, say, destabilization of the boundary of the oscillating loop or a bundle of loops or anything like this. So hence, in principle, it's a very important, say, ongoing research avenues or research topic. And so several actually very strong research teams are so very intensively developing so in that, or progressing in this direction. So now, so about actually another interesting toy to play with. About, say, 14 years after the discovery of decaying Kink oscillations, our colleagues demonstrated another regime of Kink oscillations, which we call now decayless Kink oscillations. This is just a figure from the paper of Wang et al. Published in 2012. And we can see, so it's the same time distance plot which I showed before, but now, so the displacement doesn't show any decay with time. So you can clearly see that the oscillation lasts for actually a number of cycles of the oscillation without damping. So even we can see some time intervals of the increase in the amplitude, meaning so this phenomenon is the same Kink oscillation, but which looks totally different from so the classical, say, Kink oscillation, which we got used to study. And also, so Giuseppe Nistica also published a study showing that the same loop, so which is you can trace here as a bright Raysian loop. So the same loop shows Kink oscillations in both decayless and decaying regime. So here's the time distance plot, and you can see the time running up. So, and the time distance plot shows that this loop oscillated with a very small amplitude, but without any damping. So then after some eruption, it got excited and showed a large amplitude, about a factor of 10 larger amplitude, but rapidly decaying oscillation. And once this oscillation has settled down, so again, we see the decayless oscillations. And the period of oscillations is actually, say, the same in both regimes. So the decaying decaying large amplitude oscillation and decayless low amplitude oscillations. So just repeat this movie again. You can see the decayless oscillations, which are near the threshold of resolution. So then the eruption and large amplitude decaying oscillations of the whole bundle of loops. So then the large amplitude oscillation dies, but the loop keeps oscillating with the same period, but without any damping. So it became a challenge to the, say, theorists, so because it's still actually debated what is the physical mechanism of this, but first of all, some statistical results which mainly confirm so that so this oscillation belongs to the same mode of oscillation as the decaying oscillation. So this breakdown of periods, first of all, you can see it's from several minutes, from a few minutes to several minutes. So the statistics is much, say, shorter than in the case of decaying oscillations, but not simply of, so this study was not developed by anybody. So we published in 2015. In principle now, so we can have a much better statistics, but nobody has done it. So likewise, scattering or distribution of observed cases with the loop length is sufficiently flat, but you can see the amplitudes are significantly lower so than amplitudes of decaying oscillations. If decaying oscillations is usually several megameters, now we are talking about a fraction of the megameter, so smaller than the pixel size of SDO AIA. So, but so this oscillation is clearly detected, and so these statistical properties, apart from the amplitude, so are the same or very similar to what we see in decaying large amplitude oscillations. So then the same statistics of the oscillation period versus the loop length. Again, we can see clearly the linear scaling of the period of oscillations with the loop length, illustrating that so what we see is similar to the previous regime. So the large amplitude decaying oscillations, so the King speed is about the same value. So, and again, so the data are sufficiently scattered, and actually the scattering again should be attributed to the different values of the magnetic field, different values of the density of the plasma. So, and again, so it's so may vary with the solar cycle. So, but actually, so those loops are detected during so very short period of time, so short time interval. So, meaning, so here there is no any dependence upon the solar cycle, but again, it's a future work to be done. So, but what we clearly see, so the period depends upon the loop length, suggesting that what we see is a natural oscillation of a loop as a pendulum. So the loop length determines the period of oscillations clearly. So, and why it is important? So there are actually several interesting applications, and one of them is seismology. So that's what I've mentioned before, because those decaying oscillations, so they appear after some eruptions. And in principle, what we want to have as the diagnostic outcome is the parameters of an active region, not after the eruption or a flare, but before. But of course, we can't use decaying King oscillations for the diagnostics of, say, pre-flaring conditions in the active region. So because so the oscillation itself is excited by the energy release, while the decayless oscillations, so they exist well, in principle, so all the time, say between eruptions and also before eruptions. So hence, so those decayless oscillations, so they are clearly a very interesting and promising research tool for the diagnostics of the plasma before a flare. So meaning estimating conditions which may lead to the destabilization of an active region and an eruption or flare, etc. So, and the first attempt of this work was recently published by, again, Sergei Afinogenov and myself. So this is the reference in APGL. So for the first time, we made a map of the distribution of the Alfvén speed, in an active region. So here, so the gray color scheme shows the value of the Alfvén speed in different loops in this active region. So, and so we did not actually make, so the next step, we didn't estimate the magnetic field because estimation of the plasma density is not very reliable. But in principle, so the next step, obviously, so should be, so the construction of the magnetic field map of an active region. So also here, of course, we could not link it with the extrapolation results because so the active region is on the limb, so hence extrapolation is impossible. But so it's, I think, a quite nice and say positive illustration that this seismological technique indeed could be applied to quiet active regions, meaning before eruptions. And it's another very promising and interesting research avenue. So the diagnostics of the plasma before energy releases and sort of flares and coronal mass ejections. Now, again, coming back to theory, so what can be responsible for the decay-less oscillations? Because I've shown that according to the basic theory, so even very low amplitude kink oscillations are subject to resonant absorption. So which is sufficiently solid theory, so very well understood by the research community. So, but now, so the same loop, so shows two different, actually very energetically different regimes, so decay and oscillation and decay-less oscillation, with the same period of oscillation. Strange. So now let's attempt to model it not just empirically, so from basic principles. So we have a decaying oscillation, meaning we can model, so the left-hand side is a decaying harmonic oscillator. So here A could be the displacement near the apex as a function of time. Capital omega K is the frequency of the, say, standing kink oscillation. So, and delta is the coefficient of decay, damping, which could be connected with the efficiency of resonant absorption or could be well, something else. So, so this is our harmonic oscillator, which is excited, could be excited, and then decays and oscillates exponentially and showing, say, exponential decay, consistent with observations. To counteract, so the dissipation, we may have some external force on the right-hand side. So the first guess, of course, this force could be periodic. For example, it could be leakage of P modes, which been so sometime a popular topic, or chromospheric 3-minute oscillations, or something else. So hence we have a harmonic oscillator with damping, and so the periodic right-hand side. So hence we may expect a resonance when the damping, the driving period is above the natural period of the oscillation. But so the observations actually don't support this hypothesis, because it's the velocity, amplitude, and decay-less kink oscillations as a function of the loop length.
Valery, you have 5 minutes.
Yes. So you can see this scaling is flat. So likewise, if we make so scaling with the period of oscillations, there is some increase in the vicinity of 5 minutes, but sufficiently flat, and just a few, say, outlet points so give this high amplitude. So hence, again, we can say be confident that so this scaling does not show any signature of a resonance. So hence, so the driving function cannot be periodic. So there is no signature of resonance. So hence we exclude the elusive leakage of P modes or 3-minute oscillations as a driver of the decay-less kink oscillations. So another option, so this right-hand side could be a random driver. And here actually, so we have some results which contradict each other. So first of all, so if the driver is broadband, in this case, indeed, so the response of the oscillator is a harmonic function. However, you can see, so the phase changes quite dramatically, and also the amplitude, so which is not consistent with the observations. So hence, initially, actually, we excluded this option, but in a few minutes, I'll come back to this idea. So, and the third idea was to consider this decay-less or undamped kink oscillations as self-oscillations, which are met in a number of applications in mechanics, in radio engineering. So in principle, any radio generator is a self-oscillator when a DC direct current, so like say battery energy supply, so leads to generation of oscillatory motions. So like, so a load on the conveyor belt or something like this. So, and possibly, so the best illustration is the violin. You can see a smooth and steady motion of the stick excites decay-less oscillations of the string with the period prescribed by the natural frequency. So because it's different for different loops, different strings, etc. So, and if it is a self-oscillator or self-sustained oscillator, which again, so is a very common physical phenomenon, but very rarely, say, mentioned in the context of solar physics. So in this case, so the governing equation is a so-called Rayleigh equation shown here. So, and so in principle, we can, in terms of this model, describe both rapidly decaying regime and growing and steady regime of the oscillatory displacement of the screen or of the coronal loop. So of course, so this model is say low dimensional, so it's just an illustrative model, but at least behavior of the coronal loops in this regime is sufficiently consistent with the properties of a self-oscillation, which could be illustrated by this sketch. So this is the state flow, the characteristic time much longer than the period of oscillations, which leads to excitation of say decayless or continuously reinforced kink oscillations of coronal loops. So I'm now just mentioning, actually finishing this talk. So recently we published actually another attempt to reproduce decayless oscillations by a random driver. So in this time, actually, we made one step forward. We considered a one-dimensional equation for kink oscillations. So this is the driver, which is a red noise. So you can see the spectrum of this driver. So this is the outcome. So the oscillator, which is excited by this random motion of one of the 4 points, gives, in principle, a decayless quasi-periodic behavior, and the period is prescribed by the properties of the oscillator itself, its natural frequency. So, and also we are able to excite multiple harmonics, and so this is the distribution of frequencies along the oscillating loop. You can see the fundamental mode with a maximum, or well, maximum at the apex. So the second harmonic with a node at the apex, the third harmonic, etc., etc. And what is interesting, so this modeling is consistent with observations of similar effect distribution of periods of kink oscillations in the decayless regime as a function of the slit number alone and oscillating loop. So we can see the fundamental harmonics with the maximum near the apex, and also the second harmonic, so with a node near the apex, but where the energy is mainly concentrated in the loop legs. So we don't see the third harmonic loop because we don't have enough resolution. So hence, finishing this talk, so the conclusions are, the appearance of large amplitude rapidly decaying kink oscillation, their initiation or excitation is associated with low coronal eruptions. So it is seen in about 86% of cases. So while some cases are clearly inconsistent with this mechanism, meaning so there is actually more work to be done, and there is a clear evidence of the nonlinear damping. So the quality factor does depend upon the oscillation amplitude, which should somehow be resolved. So there is another decayless and low amplitude regime of the same kink oscillation. So the period also depends upon the loop length. So it provides us with a very interesting tool for seismology of active regions during quiet periods, and especially during the pre-flaring periods in the context of, forecasting of eruptions and flares. So the amplitude of those oscillations does not depend upon the period, and the nature of the decayless oscillations is still debated. So we believe now, or at least we have a solid evidence that those oscillations are natural oscillations of loops, but actually the mechanism which leads to the constant or almost constant amplitude is still debated. It could be self-oscillatory mechanism, could be a random driver, could be some other mechanism. So here it's kind of still an open question. So that's it. Thank you very much.
Thank you, Valery. It was very interesting and concise review of very interesting topic. We are open to questions and comments. So if you have a question or comment, please unmute yourself first and then ask. Has someone unmuted? Mila?
Yes.
Yeah, go ahead.
Okay, so I have two questions. One is relating helicity. If all these oscillations are related with helicity and the damping and all these things that you showed, like how they're related with that, with the twist of the loop. And the second question is how these oscillations may be related with seismic waves on deeper layers of the solar atmosphere, say the photosphere, and maybe a possible relationship with sunquakes?
Okay, so first of all, concerning the helicity, so those oscillations actually do not manifest or are not manifested by any topological changes in the magnetic geometry. So hence, I believe so the helicity is conserved in those oscillations. So as answering to the first question. So the second question, we don't have evidence of any link of those oscillations with some quakes. However, no, in principle, if you have some rapid or impulsive energy release which excites seismic oscillations, so we may simultaneously excite kink oscillations, but possibly your question is more connected with whether the seismic wave may induce kink oscillations at a certain distance from the epicenter. So we don't have such observational evidence, but just philosophically speaking, it could in principle occur, but we don't have evidence of it so far.
Okay, other questions?
So I have a question.
CJ, go ahead.
This is CJ. Hello, Valerie. Very nice talk. So I have one question regarding the filing scenario. If that scenario is responsible for the decayeless oscillation, well, the oscillation period and amplitude depends on the velocity of the flow that's moving across the magnetic field lines.
No, first of all, if the flow is steady, in this case, we go into this violin model, so the self-oscillatory model. And in this case, so the period of oscillations is independent of the flow speed, while the amplitude will depend. So again, using this analogy with a violin, so the tune, so the frequency of the excited oscillation is independent of the speed of the motion of the stick, but the volume, so the amplitude does depend. So hence it's a natural oscillation, meaning so the frequency is prescribed by the properties of the say string,
of the string,
while the amplitude is proportional to the say speed of the motion of the stick.
Okay, thank you.
Other questions or comments? I see that for now all microphones are muted, so this gives me an opportunity to ask my questions. I have two of them. First, about this detection of the decayless kink oscillation. So you mentioned that this is sub-pixel amplitude in terms of AIA. Do you have any plan to implement something like detection pipeline to automatically detect and publish cases or something like that? It's difficult to see by eye, yes?
Yes, it is difficult to see by eye, but our case studies show that in principle, almost every and each loop shows a decayless kink oscillation in an active region. So meaning, so in principle, there is no need for such a catalog because in each active region, so we see a decayless oscillation of all sufficiently contrast loops. So the only limitation is the polarization of the displacement with respect to the line of sight. We clearly miss those oscillations which are polarized along the line of sight.
Yeah, I meant catalog, Valeria. I meant catalog not in terms of yes/no detection or non-detection, but in terms of Alvin speed and other derived parameters. This basically, yeah.
Yeah, I see. No, well, again, actually, my point is, so in principle, such a comprehensive catalog is possibly meaningless because almost every loop shows this oscillation. However, of course, it would be interesting to make it for at least several different active regions, so corresponding to, say, period different phases of the solar cycle. So such a study would be interesting, and so just comparing, say, whether there is any scaling of parameters of decayless oscillations or of the hosting active regions with so the phase of the solar cycle would be very interesting. Also, so personally, I would very much interested in seeing the difference in such oscillations in just normal, regular active regions, and also in trans-equatorial loops or say, active region loops. So this would be very interesting. So the only limitation is the manpower. However, well, I think it's a very interesting, say, suggestion. Yeah, thank you.
And Valery, and my second and last question about one of possible case study. So you mentioned, for example, it's difficult to compare with extrapolation when you see this stuff closer to limb or only or above limb. But there is a nice case, September 10, 2017, when coronal measurements of magnetic field have been made by two different methods, by standard optical using coronal rain phenomena in the paper by Kuridze, and also by our team using microwave imaging spectroscopy. So in principle, there is an opportunity to make such comparison if you have results or going to have results for this September 10 case.
Again, I would only agree. So it sounds very promising and interesting. Again, so the only limitation is the manpower. Yeah.
Okay. Any other questions or comments? I see that everyone is muted. So this means that, Valery, let me thank you again for your nice talk and thank everyone who joined us during this meeting. Yeah. So.
Good. By the way, if there are any itchy questions after the seminar, so my email is on the top of this slide. So please feel free to contact me, and so we can discuss it privately.
Good. Yeah. Thank you.
Thank you very much.
Thank you.